Morning, everyone. You all hear me okay? Hmm. How's everyone doing today? All right. Well, I'm gonna
Good.
good. I'm glad. I'm gonna go ahead and share my screen. And we're looking at Lewis structures. This PowerPoint right here. Should have already downloaded. Let me see. Yep, there it is. Okay. So there are going to be some steps that you're going to have to follow to the T, okay? Because this is a very important part of knowing how to do Lewis structures and everything else that comes after that. So Lewis structures are very important for a lot of other things. Okay, so here we go. Don't look at the chapters. I keep all or the pages. Every time we change a book, I forget to change that. So just never mind it. All right, so okay, so yeah, I know I keep drilling you on the octet rule, but that is something that needs to be followed, right? So most atoms, but this is the thing that you didn't know. I mean, yes, they're all seeking 8, but most atoms do form bonds to get 8, but there are some exceptions, and you need to recall these. There are group 1, well, hydrogen number 1, and then group 1, 2, 3, and that's it. And they get 2, 4, and 6 valence electrons. And we're talking about 1, 2, and 3, right? So A's, because that would be 1, 2, and 13 if you put just the numbers. Okay, and they get 2, 4, and 6 valence electrons. And that's in this particular case, which is known as bonding. So in this case, as you can see, if you actually look at the things that are around the central atom, which is boron, you can see that boron has 6 electrons, and boron happens to be in group 3, right? So it fills the rule in this case because it is an exception. But fluorine is not. And look at fluorines. If we go around fluorine, you can see there's 8 little dots, and each one represents an electron. And fluorine happens to be in group 7, so it's not an exception. It needs its 8. So this is how a Lewis structure usually looks. Now, I like bonds with lines, because then you can differentiate between the bonds and the lone pairs. These are lone pairs right here, right? But that's okay. You will see them either way. So that's why I want you to see both. Okay, here we go. Let's go next. Oh, I need my, oh, there we go. All right, so, and then there's those expanded objects, atoms, which we will just mention. We will not actually look at in this class, but you need to know that they exist. And some of them examples are sulfur, phosphorus and xenon. I know xenon, you're like, xenon's a noble gas. Well, yeah, but when it's made to react, it has more than 8. And it reacts occasionally, and you have to kind of force it. So, but there's sulfur. See, there's my bonds that I was telling you about. So if you actually go around sulfur like we were doing earlier, you will see that there's more than 8 electrons around it. And each one of these lines is considered 2 electrons, right? So you can see 2, 4, 6, 8, 10, 12. See, there are 12 electrons. That is much more than your 8. But fluorine is not expanding. Fluorine does have its 8, see? That's 8. And that's what we're looking at. So like I said, there are some exceptions to the rule, obviously, but mostly the ones that we're interested in, we're not going to look at the expanded octets. We're just going to look at, like I said, the short ones. And then there's these things called radicals, which we also don't look at. But if you were taking organic, this is important. And they have an odd number of valence electrons, which is odd already because electrons come in pairs. And so these are extremely unstable. That means they do not last very long. It's just like a transition state between one thing and another. So that's why we don't even worry about them either. All right, so here's the steps. When you're drawing a Lewis structure, let's write them down. Number 1, find the total number of valence electrons. And I'll show you what each step is as we progress, okay? Number 2, arrange the atoms with the singular atom in the middle. What does that mean? That means the one that there's only one of, right? 3, form bonds between the atoms. And over here, there's another little part that's not written. I don't know what happened to it, but it should say, and subtract that number from the total, okay? Number 4 is to distribute the remaining electrons so that you give each atom an octet. And that is if you have enough. If you don't have enough, then you need to form double or triple bonds. Okay? Oh, it is Lewis Structures PowerPoint on the next topic, just so you know. Sorry, I just happened to have a question on the chat, so I'm answering it. All right, so there's your 5 steps. And don't forget this part right here where I said, and subtract the number used in the bonds from the total. Okay, so let's go and apply it. Okay, so we have CF4. So we know we have 1 carbon, right? Because there's only 1. There's nothing after it, so that means there's 1. And it is in group 4. So that means it contributes 4 electrons to the pool of electrons that we're trying to, add the total. The next one is fluorine. Well, there are 4 fluorines, and it is in group 7. So when you multiply, that gives you 28. Now, it says to add all of the electrons together, so we add them, and we get 32. Okay, so that's step 1 right there. Step 2 is to place the one we think should be in the middle, which in this case is carbon, because there's only 1 of them, right? And then make bonds. Those bonds, okay, so as you can see, remember I told you each one of these lines, which is a bond, is 2 electrons. So that means 8. So we subtract 8 from the total, and it gives us 24. Now we have enough electrons to go around. And always try to put your electrons on the outer atoms. And by that, I mean not the central atom, right? So we're going to count. And you can see that there's 24 electrons, and each one of these fluorines needs 6. And 6 times 24, 6 times 4, sorry, is 24, right? So that means we have enough. What about carbon? Is carbon happy? Well, let's check him out, because we said that we wanted to make sure that carbon has its 8, right? And remember, anything that's touching carbon like that is considered part of carbon. So 2, 4, 6, 8. Yes, carbon's fine. Fluorine is not. All right. So we're going to now distribute the 24 electrons, 6 apiece for fluorine. And we should get all. And what becomes confusing for a lot of people is that we're using the one pair of electrons twice. And yes, that's why it's called sharing of electrons. Remember, we talked about that covalent bonds are sharing electrons. All right, so I'm going to go ahead and use green for the next part so that you can differentiate between them. See, there are exactly 8 electrons around fluorine if you count those. So you got 2, 4, 6, and then those 2 makes it 8. So everybody's fine. That's it. There's your Lewis diagram. That was pretty easy, right? There are some more complications coming along, of course. And the next thing that we're doing is an exception. So we have beryllium chloride. Do the same math. Beryllium is in group 2, 2 electrons. Chlorine is in group 7 times 2, 14 electrons. Add them together. Put your beryllium in the middle, make bonds. That's 4 that we just used, right? Subtract those, you get 12. Okay, so 12 electrons is all we have left. And remember, you always add them to the outer atoms first. So we add them to the outer atoms, that's 6 apiece. Chlorine is happy, but beryllium only has 4. But remember, it is an exception. So with beryllium having, oops, I don't want that color. I want the red. I want to do the red, the central atom in red. That way we'll have consistency. Okay, sorry. Beryllium having 4, right? It's okay because it is in group 2A, and 2A is an exception. You see? So it's okay. 2A can have 4. That's good. So we're done with that one. That's its Lewis structure. Okay, and you'll see what all this is about here in a minute. Okay, so let's clear those. Go to the next one. All right, the next one is going to be a little more complicated also. Each time we're going to go a little bit more, right? Okay. I will make sure I check on that 1016 lecture. Thank you for letting me know. All right, so let's see. So we were looking at carbon. Carbon times, we only have 1. So it's in group 4. That's 4. We have 2 oxygens in group 6. That gives you 12. And adding them together is 16. Put the carbon in the middle because that's the one that there's only 1 of. And make bonds. All right. That's 4 electrons that we just used. We have 12 left. Okay. So oxygen is fine. Both oxygens are fine. But look at carbon. Carbon is not an exception. And carbon only has 4. Right? So what to do? Well, you will relocate 1 pair to the middle and another pair to the middle. And that way carbon will have its 8, and so will oxygen. So this is where you do the double bonds when you don't have enough. So this is what's going to happen, watch. So you're going to take the ones I circled, well, maybe not the ones I circled, but yeah, there you go. And they went to the middle. So see, now if you count, oxygen still has its 8, and so does carbon. So that is a really cool thing about Lewis structures that you can do. Let me go back to green. Yeah, so we can see it. See, right here. So that's 2, 4, 6, 8 for oxygen, and 2, 4, 6, 8 for carbon. So that's why they get relocated. You don't have to do this every time. You only do it if you run out and the middle atom doesn't have enough. Okay. All right. So that's its Lewis structure for carbon dioxide. All right. Let's keep going. Next one is a polyatomic ion. Yeah, they do have a structure too. Polyatomic ions are characterized because they are charged, remember? So there's a little extra step to do this one. You do the same steps as before, but you also add 1 electron for every negative charge. So if you have a -3, you add 3 more electrons to the total. Okay? And if you are positive, then you subtract that 1 electron from the total for each positive. Okay? And the last thing, when you do your Lewis structure, you need to place brackets around the ion and label the charge. All right, so that's really 2 more steps. All right, so let's look at perchlorate ion. All right, so we have 1 chlorine in group 7. You should be doing these calculations along with me. That way you get used to doing them instead of just listening, because, you know, doing is a little better than just listening. All right, and then you've got 4 oxygens, right? And they're in group 6, and that gives us 24. And you notice that if we added it like this, it would be an odd number, right? Well, we don't like odd numbers because they lead to radicals, and radicals are unstable. So we add 1 more electron from the charge. You see there's a charge right here, right there. Oh, sorry, right here. See, that charge means add 1 electron. So that's what we did. Now we have 32. Now we just follow exactly as we did before. Same steps. Put the chlorine in the middle. Make bonds. Subtract those bonds. And see how many you have left. You have 24. Each one of these oxygens needs 6, and 6 times 4 is 24, so it's a perfect combo. Now, the last step is to put those brackets and label the charge. And there you go. So you notice chlorine has its 8. It has all of them. And oxygen does too. See, there's 2, 4, 6, 8. And oxygen has 2, 4, 6, and the bond makes the 8th. All right. Okay, so let's keep going. Now let's look at a polyatomic ion that is positive, ammonium. Ammonium ion, okay, so we have 1 nitrogen times 5, and we have 4 hydrogens times 1. That gives us a total of 9. But we are supposed to subtract 1 electron, and that gives us 8. Now, when we make this, you're going to be going, all right, we are using all of the electrons. Yes, that's okay, because hydrogen, remember, is an exception, and it does not need but 2. So we are good. As long as nitrogen is happy, which, as you can see, he's got 2, 4, 6, 8 total, right? And hydrogen has its 2. Therefore, hydrogen is also happy. See? And so the last step would be to put the brackets around and label the charge. And that's it. There's how you do a Lewis structure for a polyatomic ion. It's actually not anything more complicated. You just got to remember to add that charge, okay? If you don't, then you're going to get a problem with your math. All right, now, more complication. Yes, I know there's always something, isn't there? There's these things called resonance structures, which are basically another version of the same molecule. So it is the same molecule, but it can be more than one kind, more than one structure, I guess we could call it. Yeah. So in order for it to be represented correctly, you have to do all of them. How does that work? Well, it's usually because there is a double bond that can move around. So you've got to show every possibility. Like that double bond can be over here on the left, or it can be over here on the right. And that looks like the same structure, right? And it is. But having it in a different spot gives it resonance, which means it can move. And if it can move, then it resonates. And that's the word. So let's go back and see how do we do resonance, okay? So let's do SO3. Let's do this whole thing, the math and everything. Okay, let me do it in a text. And I know that you can see the answer, but so sulfur, right? We have how many? We have one. Oops, no, sorry. Let me undo that. Accidentally clicked it off. And I didn't mean to. Okay, so sulfur. We have one sulfur, and it is in group 6, which gives us a total of 6. Oops, where are you? Nope, equals 6. All right, then we have oxygens, right? Which are there's 3 of them. They're also in group 6, which gives us a total of 18. Add them together, and I'm just going to tab it over here. Oops, too far. That gives us 24, no? Okay. That's what we know. And yes, when I let go, that's going to be it. All right, so now let's do our Lewis structure. And I know you could see it better before than here, but that's okay. All right, so let's do our Lewis structure. So it says that we need to put the sulfur in the middle, and I know you can see that, but it doesn't matter. I just want you to go through the process with me. The sulfur, oops, clear. I want it red. And it is doing that thing again. I don't know why it's doing that. It hadn't done that in a while, and it's really annoying me. Where it just makes an extra, whatever it is, sulfur, see? Or it doesn't write. Sulfur, okay. And then we have 3 oxygens, so we just place oxygen, 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 and we make bonds, right? The bonds gives us 6 total. So what we had was 24, right? Minus 6 gives us 18. All right, 18 is perfect for the sulfur. But, I mean, for the oxygens, sorry, the sulfur, I meant the oxygen. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, but sulfur is going, hey, you forgot me. Why did we forget sulfur? Because sulfur is not an exception, and it's 8 too, so we need to take this one and move it here, right? So let's do that. Let's just erase it, and I'm leaving it much more bright, just so that you can actually see that that's where it came from. Okay, there you go. So as you can see, that double bond can easily be, and I'm going to make it in a different color. Let's see, just because I can, just so that you see that it could be there. Let's do yellow. It could be here, right? Or it could be here. So that means you have what is known as 3 possibilities. Therefore, you have 3 resonance structures. You see? And that's when it happens. It's only when you have an extra. Okay, so now I'm going to show you the rest of it. Obviously, it's there so you can see it, but there it is. So it says to draw them all separated by double-headed arrows. You see that? And there they are. And don't forget that when you put a double bond, you also have to take away one of the lone pairs, because that double bond, if you left the lone pair, it would no longer be 8. It would be actually 12, right? I mean, 10. I don't know how to add 10. Okay, so that's that. All right. That's how we do it. Now let's go and look at why all of this is done. Okay, so I'm going to show you where this PowerPoint came from right here. So now we're going to look at VSEPR. Before we practice, we're going to look at this because this goes with it. Now that you know how to make a proper Lewis structure, we will see what it's all about. Okay, so in order to make a proper Lewis structure, you follow those steps. But why are we so keen on having Lewis structures? There's a theory, and not, you know, remember, theories in science are not just, oh, I think so, that this is, no. Theories are things that have been investigated by multiple scientists many times, and it all points in the right direction. Okay, so that's what this is. So it is known as valence shell electron pair repulsion theory. And it states that electrons will orient themselves in such a way as to minimize the repulsion between them. So if you want to minimize anything that is called a repulsion, you want to get as far away from the other one, right? So this is what happens. If you have a linear structure, the farthest away you can get is 180 degrees, right? So therefore, the bonds will orient themselves 180 degrees away from me. You know, all the atoms, everybody, it's going to orient themselves like that. So the thing with VSEPR, it's based on two types of electron pairs. This is the whole basis of the whole thing. Of course, it has to be correct. That's the main thing. You have bonding pairs, which are the ones that form the bonds. Those are my lines. Remember, I said I like to put them as lines so that they differentiate from the lone pairs, which are the non-bonding electrons. And there, I represent them as dots. Now, you occasionally will see the bonds in the middle of 2 atoms as dots, and it's okay. Like I said, I want you to be able to see them any which way. And if you have 4 dots, obviously you have a double bond. So just got to remember that they're come in different, okay, in different notations, I guess you could say, or representations. All right, lone pairs, this is important, repel more strongly than bonding pairs. So if you have a lone pair, they will reduce the angle between the atoms, because the atoms want to get away from those lone pairs, not from each other as much. Okay, so to determine the molecular shape, this is how you do it. You are going to draw the Lewis structure. Then you're going to figure out how many pairs there are on the central atom. And by the way, here is where something that is weird. And we do not call them electron pairs. I call them areas of electron density, because if you call them electron pairs, then if you have a double and triple bond, you have 2 and 3 pairs, and they're only one thing. So they're one area of electron density, and that's a more accurate description of this. So instead of calling them one pair, it's actually one area of electron density. So the electrons are concentrated in that one area. And the shape is determined by the number of bonding pairs and lone pairs. Okay. So there are three main shapes that we're going to study. There are more than that, but I wanted to see how many there are actually in what we're doing. It's linear. Yeah, there's three main shapes. And I know it says 8, but the ones we're going to study are 3 main shapes. From there, others arise. Okay, so if you have a 2 total, right? In other words, you have 2 things around the central atom and they're all bonds, then you have what is known as a linear shape. And linear shapes are 180 degrees apart. Okay. An example is beryllium hydride. Okay. All right. There's another one. You might want to write these down, although they are in your VSEPR lab. All of this is in the VSEPR lab. Oh, and by the way, when I look at these, I call them, there's a special name for mine when I do these, and this is because I learned it that way, but I call them AB. Let me put it a little darker. Yeah, like A, for A is the central atom. That's what it represents. B is the bonds, and there are 2 of them. So this is an AB2. You see that? Because you have 1. See, the beryllium is right here, right? And these are your hydrogens. And that's your bonds, you see? So that's an A central atom with 2 bonds. See? So that's AB2. All right, let's clear that. And let's go to the next one. All right, so for that one, it's a linear. Remember that. Now we have 3 bonds, okay? So if we have 3 possible things around the central atom, right? Whatever it may be, the central atom obviously is the thing in the middle. And then the bonds are going to be, well, think of how do you divide a circle into 3 parts? That would be 120 degrees. And the name of it is a trigonal planar. So it's as if you drew a triangle on paper. It's flat. That's why the planar part and the trigonal is triangle. So a flat triangle is what you're drawing. And there's your 120. And see, there it is, BF3. So again, the boron would be right here, right? And these are your fluorines. So this is an A, B, 3. Makes it easy to remember. I like I said, I learned it this way with the A, B, and the, like that. Some people call it AX, it just depends. I just learned it as a B and an E, but you'll see why. All right, so now this is your other main shape. And when I say main shape, it's because they have no lone pairs, okay? But if you have a lone pair with these guys, then you produce a different shape. Another shape comes out from here. So the mother shape, okay, I guess we could call it, or the electron group geometry, that's what that's called, electron group geometry is trigonal planar. But the molecular shape may not be trigonal planar. In this case, it is, but it may not be. Okay, so let's look at another one. Here's one. See, this looks like an egg, I know. This is a lone pair. So here you have 3 total, 2 bond, and 1 lone pair. So how does that work? Okay, well, let's look at it. This shape is bent. So basically, all you're looking at is not the lone pair. It's just the atoms that are present. And that's why I said this comes from a molecular shape. See, molecular shape. Okay, and the degree, and it is less than 120 degrees because those atoms are trying to get away from that lone pair. An example of it is SO2. Okay, so why SO2? That sounds weird. Okay, but let me show you what happens. So sulfur, right, is right here. Oh, come on, sulfur, be better. Sulfur is right there. Then you got 2 oxygens. And this right here is your lone pair. See? So now you have 3 areas of electron density. But one of them is a lone pair. So all you really are looking at as a molecular shape now is this part. And doesn't it look bent? See? But the original shape is that trigonal planar, which looks like a triangle itself, you see? Okay, so that's what I want you to, because there is a distinction. Now, what kind of molecule is this? Well, we have a central atom, so it's A. We have a bond, how many? 2. And do we have a lone pair? Yes, so it's AB2E. E is electron pairs. See, there's your additional word. So AB2E, electron pairs. All right, let's clear all these drawings and let's keep going. All right, next one would be 4. Okay, so this is the other main shape. This is known as a trigonal planar. So if you were actually looking at it, I mean, as a trigonal pyramid, sorry. If you were looking at this, no, not trigonal pyramid, a tetrahedron, sorry. If you were looking at this, you could see that it has 4 sides. Yeah, it's kind of hard. Let me see if I can actually get you to see them, but that would be one side. The bottom over here, right, would be another side. This one over here would be another side, and this one over here would be another side. You see that? So that right there is a tetrahedron. So it has 4 sides, and they're all identical. It doesn't look identical there because it's perspective, but it is. All right, so in this case, the shape, like I said, is tetrahedral, right? And the angle is 109.5. And that is what it takes to separate themselves as much as possible. And an example of it is CH4. Again, if we were to draw the atoms, you can see that the carbon, oops, what? What? The carbon is here. Oh, I see what happened. The carbon is here, right? And the hydrogens are here, one each. And if you said this is an AB4, you would be correct because it's 4 bonds, see, and 1 central atom. Okay, so next we have the things that come from it. So this tetrahedral, okay, so linear, trigonal planar, and tetrahedral are the main electron group geometries. They're also molecular shapes. Okay, so next we have a variation of this guy. Now we have 1 lone pair, and this is what is known as a trigonal pyramid. And the lone pairs right here. Oops, sorry, lone pairs right here. Kind of looks like a friendly ghost there. Oh, like a little octopus. That's weird, but yeah. Okay, so there's your pyramid, you see. There's one side, there's the other side, there's the other side, and then there's the side in the back, which you cannot see, but yeah, that would be a trigonal pyramid. So that is your molecular shape. Now, what example we have of this? We just, okay, so the bond is no longer 109.5 because they're afraid. No, they want to get away from that guy. Kind of scary looking anyway. And an example is ammonia. Ammonia, not ammonium, okay? And if you were to draw these atoms, you can see that ammonium would be here. The hydrogens would be there, right? And this is the lone pair right here. All right, so there's your NH3. And what kind would this be? Well, A, correct. B, 3, E. See, because 1 is a lone pair and 3 are bonds. All right, let's clear that. Let's go to the next one. 1. All right, now we have another version of the same structure. Like I said, it just depends on how many lone pairs you have, but the original electron group geometry is 4. See, there's 4 things around the central atom. Therefore, the original electron group geometry is still tetrahedral, but the molecular shape is going to be bent. And this bent is different from the other bent because this bent is 104.5, like water. Water is an example of this. And let's see where water would be. Okay, so oxygen would be in the middle right here, right? Oxygen right here. Come on, oxygen, give me oxygen. There. And hydrogens would be right there. And these would be lone pairs, both of them. Okay. So the type would be an A, B, 2, E, 2. See? And that's the last one that we have here. So these are all of our shapes. Like I said, there's 3 main shapes, but many come from it. Okay, so it's all of them right here. Now, there are more, and we're just going to look at them real quick. We're not going to learn them, just so that you can see where they come from. And this is another shape right here. Hold on. When it has 5 total, and it makes a trigonal bipyramid. The angle is 120 and 90. 90 in the middle area and 90 in the middle to the upper things and 120 in the middle. And PCl5 is an example. Then there's this guy, which is known as an octahedron. And it's 90 degrees all the way through. And an example is SF6. And now let's look at this guy. Okay, so what do we know about PF3? What shape is PF3? Looking at it, okay, let's analyze. We have an original thing, right? Where your electron group geometry would have been tetrahedral, right? EEG. I'm just gonna call it, oh, sorry, EGG, electron group. Looks like egg, I know. Electron group geometry is tetrahedral. But is that our molecular shape? No. Molecular shape, and there's no MSG. That sounds like something you put in food. Molecular shape is actually not. It is trigonal pyramid. Okay, see? And how can I tell? Based on the 2 things that we know, that this is an A, B, 3, E. See? And we also know that the shape itself See, this is why I like the AB3E, because that right there tells me central atom, 3 bonds, 1 electron pair. And you can just go back and look at them and say, oh, yep, that's what that is. And you'll be correct. So let's go back to the other PowerPoint and see if we can tell if there's still no more. I think there are no more on this one. Oh, no, here's another one. Okay, you can tell that one's linear, right? Those are models, the space filling model and the sticks and balls model, I think is what it's called. All right, so let's go to the other PowerPoint that we just did. So back to the Lewis structure one and see if we can tell the shapes now that we know. That'd be kind of cool. Let's see. All right, I'm going to erase this here in a minute because this is in the wrong place. Okay. Clear. Okay, so let's go to, just to quickly, come on, why on earth did you do that? Sometimes I tell you. Just clicked on that and it went away. Okay, so let's not do these. Okay, okay, there we go. Let's do the first one, okay? Just want the shape. Okay, so what shape would this be? All right. We know that it is an A, right? Because it has a central atom, B, and we got 1, 2, 3, 4 bonds, so AB4. Therefore, this is tetrahedral. I'm just going to not spell the whole thing, but you can get that. All right, so we got that one. All right, I'm going to let you guys do one here shortly. All right, let's see what's next. All right, who wants to do this one? Just kind of call it out. This one's easy.
Is that linear?
Correct. Because you can see it's an AB2, right? A central atom with 2 bonds. Correct. Linear. All right. What about this guy?
Also linear.
Also linear. Correct. All right. Let's look at this next one. What is this one?
The tetrahedral.
I'm not gonna lie, I'm kind of lost.
You got it. Tetrahedral is correct. Okay, so what you got to pay attention to is what's there. So it's 1 central atom, yes, with 4 bonds. So that's an AB4. AB4 equals tetrahedral. Okay, what about this guy? Tetrahedral is correct.
So if it's 1 central atom with 4,
Mm-hmm.
I'm trying to write this down, sorry.
Yeah, that's fine. Okay, what about this guy? And I know he's resonance, but he has a shape, just like the other ones, right? Or it has a shape. I always put male and female things. I don't know why. Must be my Spanish background that I always give him a gender.
It's the one that's like got the triangle.
So a flat triangle, yes, which would be trigonal planar. That is correct. All right, see, you guys got it. All right, now let's do a little practice. See right here, we're not going to do this one yet. We're going to do this one. And all we're going to do is do the whole thing as we've been doing. And you'll see. It is, we're not going to do the whole thing, obviously, but you don't have to actually take any notes because I've given you all of it right here. Even how to how to do the entire thing right here. See right there. See how it's telling you 2 electron group geometry. See, this is just electron group geometry, which is what I was telling you. That's the main shape. But then there's those that branch out of there. Cannot pull it up. Okay, see, there it is. I gave you the whole entire table. So 2 electron groups, 2 are bonds, then it's linear. If 3 electron groups and 2 are bonds, then it's trigonoplanar, but the molecular shape is bent. You see that? If you have 3 and 3, it's trigonoplanar, trigonoplanar. If you have 4 and 2, it's tetrahedral, but it's bent. You have 4 and 3, it's tetrahedral, but it's trigonal pyramid, and 4 and 4, yeah, it's in 4 bonds. We're talking about 4 bonds. And then that's your, see, you can tell that these are the original ones because they're the same when you are actually looking at the molecular group geometry. They're all the same. You see that? These are your 3 main shapes. These are your 3 electron group geometries. Right there. Now, from there, the other ones arise. Okay? All right, so let's go and do a little practice. And this one, I'm going to draw the Lewis structure on the side. Okay, that first one is drawn, and you notice it's all filled in, right? And that's okay. And we're going to do the polar, nonpolar later. But for now, I just want you to be able to do this part. All right, so if we did the math, you would see that there's 1 carbon. And let me get my spotlight. Okay, here we go. 1 carbon times 4, right? Because it's in group 4, plus 4, because we're doing CCl4. So 4 chlorines times 7, total of 32. Then we do the bonds like this, crude sketch. We subtract the number of bonds. In this case, they put 4 times 2 so that you don't get confused where 8 came from, but it's 4 bonds times 2 electrons apiece gives you 24. All right, and that's that. So now you know you've got to put 6 around each one of the chlorines, and carbon's happy. So we're done. Now you can see that this is an AB4 because you got 4 electron groups. The geometry is tetrahedral. The number of bonded atoms is still 4. See, nothing changed from here to here. And then you've got the molecular shape being tetrahedral also. The bond angle being 109.5, and there are no resonance structures. And that's where we stop, okay? So let's do BF3.
Wait, I have a question.
Yes.
How do you know if the central atom is like happy, as you say, or if it's not happy?
Okay. It's happy. Okay, there are some exceptions. Like I was about to show you one just now, but that's okay. Look, see right here? See this chlorine? Ooh, I barely see the yellow, but you can see that, right?
Yeah.
Okay, how many atoms do you count in that circle that I just, well, sort of circle that I just drew?
The little dot?
No, inside. Inside that circle.
4?
4 times 2, right? Because each one of those represents what? A bond. A bond is 2 electrons. See?
Oh, okay, I get it.
Okay, and now look at the other guys. The sometimes this thing doesn't want to give me colors. I want to do the green color. Okay, so right here. Oops, I don't want to go all the way as, there we go. Okay, how many do you see around chlorine?
8.
Exactly. So that's what we're looking for, 8 and 8. Everybody's happy, you see. Now, there are some exceptions that you have to remember, like what we're about to do right now. So I'm going to go ahead and type in the numbers. So we have 1 boron, right, times 3, plus we have 3 fluorines times 7. Oops, that sounded good. Sorry, I had my cap logged on. I'm sorry. equals. So 21 plus 3 is 24, correct? All right, so we draw our bonds. I can't do them small like that, so I'm going to have to do them really big. You guys can put them in small if you want, but I'm going to have to do them really big. So I'm going to do them in blue. Okay, so boron, and then we have fluorines, right? 1, 2, 3. Okay, so we know that we have, from there, we need to subtract. Okay, let's see here. Okay, so we have 24 minus. The reason we're saying minus is because we just used 3 pairs of electrons, right? That gives me 18 so far, right? You agree? Good math? Maybe not so great math, but it's there. All right, so now what do we need to do? Okay, we need to distribute those 18 electrons. And remember, we always start with the outer atoms. So we're getting 6 on that one, that makes it 8 total. 6 on this one, that makes it 8 total. 6 on that one, also 8. So that means a total of 18 electrons we used. And boron's not going, hey, why did you forget me? No, boron's fine because boron is an exception. And even though it only has 6, it's happy because it's the exception of group 3A. You see that? Yeah? Okay, so you can put this right here, this little Lewis structure right there. Okay, but I'm going to leave it like it is for now. I'm just going to undo that thing and that and that and that. There we go. All right, so now analyzing this Lewis structure, how many electron groups do you see? And that means around the central atom. So we got 1, 2, 3. That's right, because we got 1, 2, 3. Just the central atom. You don't have to look at anybody else. So that is 3. All right. So that means our structure is going to be trigonal planar, right? Our electron group geometry. Now, how many are bonds? 3. That means this is an AB3. And the molecular shape is the same as the electron group geometry because nothing changed. Okay. So the angle, all of it is in that one table. So you can go look at the table in a minute. Oh, and we have no resonance because we have no double bonds. Okay, so let's go look at our table. And just keep in mind that we know we have 3 electron groups and 3 are bonds, right? So let's look at the table. Actually, we're bringing the structure with us, so that's good. All right, look at the table. 3 electron groups, 3 are bonds, trigonal planar for the electron group geometry and trigonal planar for the molecular shape. There's your AB3 and there's the 120. You see, all of it is right there in that one table. All right, let's trash that one and let's do another one. If we still have time, do we still have time? A little bit, right? We have about, what, 8 minutes or so? All right, let's look at the next one. SO3. Let's do the math. Okay, so we got 1 sulfur, right? And it is in group 6. Plus, we have, oops, not minus, plus, we have 3 oxygens, which are also in group 6. That gives us a total of 24, yes? Okay, so when we do this crude sketch, and I'm going to do it right next to us, right there. So hold on. Okay, so S, O, O, right? O, O, O. Okay, we know we just used 6 electrons. So we take 24 minus 6. Well, okay, minus 3 times 2 is how they do it. So 3 times 2. And the reason I'm doing it like that is so that it follows the same pattern. So that's minus 6 gives me 18, right? Okay, 18 electrons is good. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so that's 18 electrons. Is sulfur an exception? Not in group 1, not in group 2, and not in group 3. So no, it's not. So remember our little trick of moving one of these to the middle? So that's what we have to do. So let's undo those. And let me just erase that one. And now put the double bond. And I'm going to make the double bond thicker so that you can see that it came from there. Okay, so there, that's our shape officially. All right, so what do we see? We see that is our exact Lewis structure right there. Nothing different. Okay, so we see we have 3 electron groups, right, around the central atom. Remember, electron groups meaning doesn't matter if it's a double, triple, single, whatever bond, or a lone pair. Any of those is a group. All right, we have 3. So that means this is again trigonal planar, right? We still have 3 bonds. Oops. Come on, 3, which means it's an AB3, which means the molecular shape is trigonal planar again. Planar, okay. And the angle is 120. And do we have resonance? Yes, we do. 3 resonance structures, because this can be 1. Oh, hold on. This can be 1, this can be 2, and this can be 3, right? Because that double bond can flip from here to here and to here. So we have 3 resonance structures, and we'll leave it at that. All right, let's trash this one. CO2. All right, let's do the math. And like I said, it helps if you guys go along with me. Maybe I'm going too fast, but 1, and carbon is in group 4, so times 4, plus we have 2 oxygens in group 6. That is 12 plus 4 equals what? 16, right? All right, so now let's do them. The quick Lewis structure, which is known as your crude sketch. So let's do it down here so it'll fit. All right, so we got COO, right? So from that, we can see that we just used 16, we subtract 2 times 2, right? Which gives us a total of 12. 12 electrons to put around all of the atoms, all right? Let's see. All right, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Carbon's going, oh my Lord, you forgot me. We did. So we need to move a double bond. I mean, a lone pair as a double bond, and then count and see if we got enough. Okay, so far carbon has 6. No, not enough. All right, so, and people go, why don't we make a triple bond here? And that's a good question. But usually triple bonds don't form as easily. So a double bond is better unless you only have one choice. And in this case, we don't. So there it is. There's your structure. So you can see that's a linear, right? Because there's only 2 things around the central atom. So we're going to say there are 2 and this is linear. Now, they're both electron groups, so that means this is an AB2. And it's still linear, and the angle is 180. And there are no resonance structures because the double bonds are in both places. If it was just one double bond, then we would have two. But they're both double bonds, so they can't move. If they move,
So why does carbon need 8?
because it's not an exception. All of us need, all of us, listen to me, all of them need 8. Every single atom needs 8, except those exceptions that I told you at the beginning. And
Okay, I think because my thing was messing up, so I joined late, so I missed the whole
okay,
8.
okay, the exceptions are groups 1, 2, and 3.
1, 2, and 3. And
8.
they all 8 except for 1, 2, and 3.
Yes.
Okay.
Like 1 will only take 2, 2 will only take 4, and 3 will only take 6. Like boron. Like when we did boron right here. Remember we said it was okay with 6? Yeah. All right.
Okay.
That's not an exception, therefore it needs its 8. And both of them have 8, as you can see, now that we rearranged it. And that's the key to this, is that you rearrange the atoms accordingly. All right, so let me undo those extra lines. And let's, oh no, actually that's it. That's it. We're done with that one. All right, last one. This one you're gonna like because it's totally different. So far we've had nothing but the same, right? But this one's not. This one's a little different. Okay, so we're gonna say we have 1 atom of chlorine, which is in group 7, plus we have 2 atoms of carbon, which are in group 6. That gives us a total of 1 plus, 12, that's 19, right? Yeah. But we also have an extra electron, which gives us 20. Remember the negative needs to be added. Okay. So now if we did the math, now the Lewis structure like we're supposed to, we would see that chlorine, ooh, what in the world is that? I don't know, but that was not pretty. Okay, come on, chlorine, give me what I need. All right, so chlorine and oxygen, right? Like this. All right. So we now need to take from those 20, right? We subtract 2 times 2, which gives us 16 total. Yes? All right. So let's start putting our lone pairs, always on the outer first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, look at that. We had just enough. We don't need double bonds. You see, sometimes you do have enough. All right, so with this Lewis structure, we know this is where we know what we know. We have 4 things around the central atom, right? And by 4 electron groups, we mean 1, 2, 3, and 4, right? These lone pairs, 2 lone pairs, and 2 bonds. That's 4. All right, and this structure is going to be tetrahedral, the electron group geometry, because there are 4 things around it, but only 2 of them are bonds. So then this is an AB2E2. That means you have 2 bonds and 2 lone pairs, which makes this bent. And the angle 104.5. And there are no resonance structures because there's no double bonds. You see how it changed a little bit? And you can look it up. Okay, so let's go look at 4-2 in our chart. There it is. Okay, so 4 groups two of which are bonds, is right here. Let me highlight it a different color. Right here, 4 groups, 2 of which are bonds, is tetrahedral, bent. There's all the information right there. You see it? And see, you can see it on this Lewis structure for sure. There. I wish I had made it so that you could see it all in the white, but that's okay. You can still see it, okay? So yeah, that's a better place. So you can see there's, let me look at the central atom. Okay, so we're only looking at central, remember. The other ones are just to guide everything to the central atom. Okay, so looking at the central atom, you can see there's 1 bond. And see, this is why I like to put lines instead of dots, because it can get confusing if you put dots there. And these are 2 electron pairs, which is what this is. If you look at our green highlight, 4 are electron groups, 2 are bonds. So it's a tetrahedral in electron group geometry, but it's bent in shape. Okay, and the angle is 104.5. So that's how you would do all of them. And if you want to practice, because this is one of the best things you can do, is practice. You can try doing the rest of these yourselves. See if you get them. I will show you the answers next time, but see if you get all of these. There's a total of 20, so I did 5. You've got 15 more. And you don't have to do all of them, but I mean, if you want to learn better, then that's what I would suggest you do. Sorry, this one needs to be below. Okay, there we go. So see, there's some. And then we will learn, next time we'll learn about polar, non-polar also, and how to put the intermolecular shape, forces with the shape. And it's easy. You will go, oh, that's the easy part. It is the easy part. Believe me, very easy. The polar, non-polar, super easy. But I'm not telling you just yet. We first have to learn to make that Lewis structure, because that's important. Everything comes from it, as you can see. So if the Lewis structure is wrong, all your answers are wrong. So that is why this is so important to do. And there are step-by-step instructions here also, right here. Hold on, where are you? Table. There it is, right there. See? You can do 1, 2, 3, 4. So they're all right there too. And it's giving you an example of one as they do it. So where are you? I passed it. There we go. See, it even tells you hydrogen requires 2 electrons, boron require 6, and other elements require 8. See? But boron's not the only one. That's okay. Beryllium too. So, and if the central atom lacks an octet from multiple bonds, except for the exceptions. So there you go. There's some other examples. Okay. Let me know. All righty.
Thank you.
You're welcome. So I'll be posting this shortly, and I will make sure that one on the 16th, was it, that you talked about, Sam? I think it was. Yeah. No, Valerie. Sorry, Valerie. 10/16. Okay.
Yes, ma'am.
Okay, I'll have to go look at it and make sure I have it. If I don't have it, I'll post the one from because I have another class also that meets. Yeah, so I can do that one instead.
So
Maybe
we're
it
all
just
done
didn't
with chapter.
record.
Is now the next
Oh.
chapter.
I'm sorry?
I said we're all done with chapter 7. This is the next chapter.
Correct.
Okay.
Correct.
Okay. I have 1%, so it's about to die. But thank you.
Sure, no problem.
Bye.
Thank you.
Mhm. Guys, have a good day, and I will see you Wednesday. Well, I'll talk to you Wednesday.
Okay.
All right. Thank you. Bye bye.
You're welcome. Bye.